Hello. Let us start the same. So yesterday we have been seeing one small example, right? So from there we'll start today's class, and then we'll continue to the space complexity as requested by Raj in the group. So we'll continue with the space complexity, and then we'll go to our actual class. Okay. So I'm going to write a small program for the time complexity. For the same time complexity, it was discussed earlier in the class. So I want you to calculate the time complexity. This is not to test you guys or something. This is to, assess. I mean, if whatever I'm teaching, is it going to you or not? It's just assessment to me. Okay. It's not for you. Okay. Let me kind of, okay. Let me think over. So, okay, for today's class and tomorrow's class, just for this algorithms class, just have a paper or book and a pen. Okay, always. So p is equals to 0. There's no need for you to take the notes, but at least for the calculation purpose, you need it. For I is equals to 1, I less than n, I is equals to I times 2, and p plus plus. For j is equals to 1, j is less than p, j is equals to z times 2, and some statements which are irrelevant to a time complexity calculation. Okay, so now tell me, what is the time complexity of this? So once you're ready with the answers, please let me know. I'm looking into your chat box. So I need both of you to answer those, answer the of time complexity of this algorithm, and let me know. Okay. So how about Raj? Okay. So this is nothing but 1 minute. So this is nothing but login. Just give me a second, guys. Okay. So yeah. So so this time complexity of this particular block is login. That is right. So that is what Aravind has told. Like this is O of login, right? Is that right, Aravind? O of login, and this is log p, right? This is log p. Log p. Okay. So if there are if there is some common point in both of this is absolutely right. O of log n plus log p. I mean, you should not say O of O of log n plus log p. You can tell like this, or even what you can do is that. So you have to see if this p can be expressed in terms of n, because you have a connection between a p here and here, right? So in this particular case, what you will do, you will just try to say, since p is expressed in terms of log n, so that makes it log of log n, because p is nothing but log n. So log of log n. Clear? Both of you. This answer is right. Whatever you told me is right. But still, you can always do in this way. Okay. Clear? Both of you? Okay. Clear. Okay. So fine. So performance of an algorithm. Right now we are looking into the performance of an algorithm, right? Performance of an algorithm can be calculated in terms of two things. So one is time complexity. The other one is space complexity. How much space the algorithm is occupying. How much time does that algorithm take to finish that particular task, right? These are two things. These are two parameters a algorithm is being assessed. Depending on these two parameters, an algorithm is being assessed. So as you know how to calculate the time complexity. Now let me explain you how to calculate the space complexity. So what is space complexity? Space complexity is nothing but how much extra space your algorithm takes to solve that problem. how much extra space does that algorithm takes? For example, you have a function, let's say you have a function, let's say it's add function. Okay, add. Space complexity. So you have a function called as add of a comma b. So sum is equals to a plus b. You'll return this sum. Yeah. Okay. Now tell me, let's assume a and b are integers. So even in Python, there are, see, Python, JavaScript, I know there is no concept called as integer. I mean, there are there is a distinction between an number, float, and everything in Python. Same way that stands to the JavaScript as well. Both are scripting languages. So I know there is no something called as integer data type, but when you whatever the value you store in variable, that variable type becomes int, float, or something, right? So that right? So let's assume, for simplicity's sake, it's all integer. See, I'll give you a clear difference between a compiler language and the interpreter language. So in compiler language, you always try to initialize those variables, whether it is an integer type, or it is a float type, or it is a string variable, whatever it is, you give it. When the same time, when you come to the scripting side, you don't specify the type of the variable, but the interpreter will allocate the memory by knowing the value that is being stored in the variable. For example, let's take Python or JavaScript, whatever it is, in both the languages. Whenever you say a is equals to, what happens now? If you perform this statement in Python, type of a, it says int, right? So when you store a value of 2.2, when you say type of a, it says it is float. So now you should know the difference. The only difference between the compiler language and the interpreter language is that interpreter language will allocate the memory on run, on the flow. It allocates. But compiler does not do that. It always compiles first and then runs. That's the only difference. So Python, on the run, it decides what kind of variable is that, what should we do, everything. It is something like, in compiler language, you have lots of headache knowing the type of variable, making it, and then typecasting it, everything. That is a big headache in the compiler languages. But on the run languages like interpreter language, you don't have that headache. So everything will be dealt by interpreter. That's the reason why interpreter languages are like kind of in boom, because the time to market is really very less. So whatever the code you want to run in Python, whatever the code you want to like develop in Python or JavaScript or in any interpreter languages is very easy, because there is no such kind of attacks. It is just only you are trying to write your business logics and you're executing it. Okay. Why I'm telling all this? Because you shouldn't think Python or JavaScript is completely, independent of memory. Even those kind of things also by at the kernel level, they do it. At the user level, we don't do it. That's the only thing. That's the only difference. Okay. So now coming here to the space complexities. Okay. So let's assume this as integers. And let's say so each integer is of 4 bytes. So sum also an integer type. So how many bytes this sum is going to take? 4 bytes. Some variable is going to take 4 bytes. So return sum. So this is going to return. So how many total number of bytes this function is using? How many bytes this add function is using? So you have a, b passed as a parameter. You have variable sum, which is used by this function. Sum is equals to a plus b. So the result will be stored in the sum. So sum is going to occupy 4 bytes. So totally add function is going to utilize just 4 bytes of memory. So A and B are passed as parameters. So A and B are allocated somewhere outside this function. So A and B is not considered as the memory. Inside the function, only sum is being utilized. So I'm creating just the sum. Sum is initialized here. So this add algorithm is going to utilize this sum. See, so let me ask you this. Int A, okay? Int A is equals to 4. If A is equals to 10, so how many bytes of memory this A is going to utilize? How many bytes of memory this A is going to utilize? Forget about everything. Just tell me this. You have int A is equals to 0, A is equals to 4. So let's assume int is going to occupy 4 bytes of memory. Okay, how about A is equals to 100? Ravin? Now? Ravin? Cool. So now you understand this memory concept, right? Okay. So in this add function, this A and B. So let me do this so that you will understand. Main function, A is equals to 5, B is equals to 5. These are integers. When I declare this as 5 in an interpreter, it becomes integer. So don't worry about this main. It's just an algorithm language, algorithmic pseudocode. So I have sum is equals to A plus B and return sum. So print or display this A add of A comma B. Okay. So how many bytes this function is going to utilize? So what is the variable it got initialized? What is the new variable here in the sum? A and B is already declared here, so don't consider this. Yes, it's just a sum. So sum is nothing but 4 bytes. So what is the space it is being utilized? This is just 4 bytes, which we call it as, it's a constant, right? So even in the runtime complexity, whenever we say if A is equals to B, what is this? What is the time complexity of this function? Sorry, what is the time complexity of this for this statement? What is the time complexity of this statement? Aravind? Of 1, that is constant. So in the same way, if it is a constant byte, we call it as O of 1 space complexity. It's constant. So usually we calculate the space complexity in terms of auxiliary space. I'll tell you what is auxiliary space. Auxiliary space plus variable, fixed variable, that is fixed variables plus dynamic variable. Okay. So what is A? Is this dynamic or fixed? A and B, what is this? Both of them, are they dynamic or fixed? Fixed, right? So what? How about sum? Okay. So Raj, dynamic means so it should be like number of bytes should increase dynamically. For example, if you take array of size 1, what is the space of array of size 1? Let's say array int array. Okay, let's say it is an int array. What is the space of 1? What is the size of this array? How many bytes this array is going to take? How many bytes? 4 bytes. If I make it as 2, how many bytes it is going to take? Int array of 2, is that 4? It's an array of 2. If it is an array and if it is int, so if it is 1, it is going to take 4 bytes because it stores only one integer value. If the same array, if we initialize that with 2 integers, then it is going to take 8 bytes of memory. If it is 3, then how many? Aravind? 12. Okay. So what is this? This is called as dynamic variable. These are called as dynamic variables because the size of the variable can be increased. It can't be decreased though. You can increase, but in C++ in some language you can decrease, and even in Python we can decrease. I guess, yeah, we can decrease. Okay, fine. So let's think this as dynamic variables. Okay, these are dynamic variables. So whenever you're calculating the space complexity, you consider auxiliary space. I'll tell you what is auxiliary space, but as of now, don't worry about auxiliary space and the dynamic variables and the fixed variables. In the previous example, there is no auxiliary space required. There is no dynamic variable. There are just fixed variable. So total space complexity, total space is 4. So space complexity would be constant O of 1. Clear? I'll tell you what is auxiliary space. Don't worry about that right now. So there is no dynamic variable. You agree? There is no dynamic variable in the previous example of add. So they are just fixed variables. So I just sum. So it is of 1. Clear? Both of you. Raj? Okay. It's very simple. Okay, you have to have your basics right. You have to just stick to your basics. Always have strong basics. Okay, that is the key. That is the key in algorithms. Fine. So, auxiliary space. So auxiliary spaces are considered only in the recursive functions. Are considered in the recursive functions. Okay, so don't worry about this auxiliary spaces. We'll cover those in recursive functions. And how about, so dynamic variables are nothing but your arrays or whatever it is dynamically, whatever you are allocating dynamically in the function, those are called as dynamic. I mean, those are called as dynamic variables. You already know the fixed variables. Okay, cool. So now I have one more example. Let's see. So this is some array. This n tells you that let's have just n. Okay, so this, okay, let me make it as n1. So I'm just iterating the array and having a sum, returning the sum. Okay, what is the space complexity of this? If you want, I can just take this off. This is not required. Okay, tell me what is the space complexity? In this example, consider this as an integer array. Of 1, okay, 28 bytes. What is 28? What is 28? What is the space complexity? Raj, what is the space complexity, Raj? Of 1, okay. Right. So I have one function. Okay, I have one function. So this function takes array as a parameter and it initializes one more array. Array 1 is equals to some blank. Okay. What it does is that it just copies whatever in array to array 1. For n in array, don't worry, don't think like, whatever I'm writing as an example, there is an alternative approach. It is not, this is not a class for having the best approach. This is just a class where you can understand the space complexity. Okay. For n in array, just copy this array 1. So array 1 dot, okay. Please forgive me. I'm just writing all the syntaxes. Okay. For n in array, it is just copying. Let me write. Yeah. Array 1 dot copy. Just copying this n. N is nothing but element in an array. And then that's it. It just does this. Tell me what is the space complexity. What is the space complexity of this algorithm? How many fixed variables are there in this function? How many fixed variables? How many fixed variables in this function? 1. What is that? Okay. Aravind? Okay. So we don't know the size of the array. This is just copying an array to another array. We don't know the size of the array. This array can have any number of elements. It can have n number of elements. So is this array called as a fixed array? Is this a fixed one? Is this array a fixed array? Is this a fixed variable? For example, in JavaScript, for example, in Python, this is a list. Okay. This is a list 1. I'm having this. And let's say this is a parameter. For everyone. Okay. So I've written a small function in Python. Now tell me, Arvind, is this L1 a fixed array, fixed list? How many elements you can store in this L1? Is this a fixed array? Raj, is this a fixed array, fixed list? No. So this is an dynamic variable. Accept, agreed. N is a fixed variable. Okay. So there is no auxiliary space because we are not calling this in a recursive manner. So we usually don't consider auxiliary space. What is the space complexity? So the space complexity would be O of n plus O of 1, which is almost like O of n. Clear? Both of you. Raj? Okay. So this is how you calculate the space complexity. You always calculate the space complexity. How you will calculate this space complexity? Just calculating the variable which is declared inside that algorithm, that function, or that anything, procedure, whatever you call it. Okay. So if you see in Google for space complexity of a linear algorithm, linear search algorithm, it always says O of 1 because the array is passed and the search element is passed, and linear search, what it does, it will just see for n in array, if n is equals to k, returning those index or whatever. If this linear search returns index, then what we'll do, return for n, I enumerate this array. So return that index. So what is the space complexity of this? What is the space complexity of this algorithm? So you want me to write clearly? I'll write it. So def linear search array and the search element. So for n in array, if k is equals to n, return found. Okay, sorry, return found. Then here return not found. So tell me, what is the space complexity? What is the space complexity of this linear search? What is it, Arvind? How it is O of n? Can you unmute yourself and talk, Arvind?
Yes, sir. Hello.
Yes, Arvind. Go ahead.
Yeah. So because array element which is being passed as a parameter, that is because it is a dynamic variable, and the length of it could be anything, but k is an element we are trying to search within that array, and that is being a fixed variable. That's why I'm thinking that
Okay.
because the array.
So the way you told me everything is right. The only difference is that array is a dynamic variable. Don't consider the parameters. Only see if there are any variables that is being declared inside the function. Is there any variable that is being declared here?
No.
No, right. So here we have one, we have one iterating variable here. So we call it as iterating variable in Python. So it's just a variable. Let's talk. I think Raj is in JavaScript guy, so I'm talking in something. So it's just a variable. It's a fixed variable. So let's say it is 2 or 4 bytes, whatever, depending on the system. So, and then probably the string. So probably the string might occupy, let's say 16 bytes, both of them, like 4 bytes, 4 bytes. Or this is 1, 2, 3, 4, 5. This 5 bytes. This could be some 16 bytes. I don't want to count this. Okay. So totally, what is it is all constant, right? All are constants. So totally it is of 1. Clear, Arvind?
Yes, sir. Yeah.
Clear? For suppose,
yes, because
if I create an array again here, if I copy this array or do something with this, okay, then it is O of n. Clear?
Got it.
I don't do any. I don't have any array here, so it is O of 1. Space complexity. This is space complexity. Okay, don't forget that this is space complexity. So what is the time complexity of this? What is the time complexity? Arvind, what is the time complexity?
Yeah, that will be O of n.
Yes, cool. Okay. Raj, are you clear? Yes, okay. Okay, so now let's talk about the auxiliary space. So auxiliary space comes into picture whenever you are doing some kind of recursive functions. So for example, there is a function. Let's say it is foo of n. If n is greater than or equal to 1, what I'll do is that I'll call this function foo of n minus 1, and I'll do a display of this n. There's nothing but print, okay? Display of the 10. Okay. So what happens now? Recursive, what it does is that the interpreter or compiler pushes everything into a stack. What is stack? Stack is nothing but your last in, first out. So it pushes some information into the stack, and then it retrieves that. So what is that? So first, if I call foo of, let's say 2, okay? If I call foo of 2, what happens? So first, so in each of the stacks, it's a stack. So in each of the stack, what happens? It will put an information about those parameters and the information about the local variables, and it also puts the return address. So to where it has to return. Okay. So this is called as activation. This is called as activation record, or simply is also called as stack frame. So whenever you write a recursive function in Python, if the recursive function is not good, it is just like recursing the function for, like, you know, if the code breaks or if it goes to infinite recursive, you will get an error called, you know, out of stacks out of something, right? So this is what it does. What happens is that it creates a stack, any programming language, nothing to do with interpreter or compiler. As I told you, the only difference between compiler and interpreter is here interpreter will take care of its memory, everything, whereas in compiler language you have to take care of it. So here the programmer does the programming with with less tension, less burden with the interpreter languages, whereas in compiler languages, it takes more burden by considering all the memory, what variable, all those things. Okay, right. So here, let's see what happens here. So this is called a stack frame. What is stack frame? Stack frame is a combination of parameters, local variables, and the return address. So lost in first out. Okay, this creates a stack and puts this here. So first it checks if n is greater than 1. Yes, n is greater than 1. Foo of n minus 1. What is foo of n minus 1? That is nothing but foo of 1, right? Foo of 1. So what happens now? Just creates foo of 1 here. And with the other things, local, what are the local variables and everything. So first, okay, first let's say it calls foo of 2 and then foo of 1 here. First it puts foo of 2 and then foo of 1. And then what happens? Just puts foo of 0. So now what is stack? Last in first out. So first it clears this. So it foo of 0. Is that n greater? Is that 0 greater than or equal to 1? 0 is greater than or equal to 1? No. So it does not do anything. It clears this. So whenever we are putting this foo of 2, it is called as push operation. Whenever we are taking out, it is called as pop operation. So since it is a stack, we do last in first out. So this is the last appended thing, right? Foo of 0. So we take out. So we see there is no, there is nothing to do. So we remove this. What is foo of 1 here? Foo of 1, yes, 1 is greater than or equal to 0. 1 is greater than or equal to 1. So now what happens? Foo of 1. What happens? It goes inside. It creates another, it appends one more stack called as foo of 0. Okay, so already we created. Okay, foo of 1. So let's see what it displays n as 1, and then it comes out. So what is foo of 2? It goes here, it displays 1 and 2. Okay, now the question is, so how to determine? So here, if you see, if I calculate the space, if I calculate the space complexity by just with this functionality, is there any variable that I've declared here? Anything inside this function? Did I declare anything? Did I declare anything inside this? No. So usually the space complex should be O of 0, right? But that is not this. This is not one. This is not the right answer because it has created some space. How? So for each and every function, it has to, it creates an auxiliary space. It creates an auxiliary space in the stack. So how the stack memory, how many? So for 2, I occupied 3 frames, right? So let's call it as frame. I occupied 3 frames. For 4, I would have occupied more frame. So that means what is the space complexity of this algorithm? What is the space complexity of this algorithm? Exactly, right. O of n. So now you should always consider the auxiliary space when you calculate this kind of recursive functions. Clear? So now you understood why it is O of n. It is because of this stack. So stack memory, that is nothing but auxiliary space. So that's why whenever whenever you try to do a recursive function, if it fails, you get like out of stack kind of problem. I don't remember exactly what is the error, but you get something on the lines of stack. It is clear. You should be very clear on time complexity and space complexity. Can you hear me? Can you hear me? It's okay.